explorers are sending startling data back to Earth. Explorer 1, NASA's farthest voyaged space apparatus, continues to traverse revealed regions of the universe almost 50 years after its launch. Researchers are bewildered by the surprising realities this iconic spacecraft is transmitting to Earth. What seems like a glitch is part of a complex communication as we analyze the unique records sent back during its space investigation. Researchers have been engaged in advanced studies regarding the universe's past since the Big Bang, driving the launch of Explorer 1 and Explorer 2 among various missions. Explorer 2 was the first spacecraft to launch, departing from the NASA Kennedy Space Center on August 21, 1977. Explorer 1 followed 2 weeks later, on September 5. Despite being launched as twins, they have followed different trajectories. Both probes weigh 720 pounds, roughly comparable to a small vehicle, and were launched during a long window that took advantage of an interesting planetary alignment, creating a slingshot effect to send them on their journey. On December 15, 1977, Explorer 1 was able to sidestep its identical twin. Since then, it has served as our go-to source for contemporary records in space. The first spacecraft to achieve this feat was Explorer 1 when it began its Jovian imaging project in 1978, around 265 million kilometers from Earth, sending a substantial amount of images back to us. In January 1979, Explorer 1 completed a remarkable 108-hour stint, capturing 3,750 photos of Jupiter's rotation to create a time-lapse film showcasing 10 frames of the planet turning. It passed through the Jovian moon system in February 1979 and discovered the small rings surrounding Jupiter a month later. Explorer 1 also made significant revelations, identifying new moons named Phoebe and Matisse. Precise maneuvers were executed to ensure the spacecraft was ready for its flyby of Saturn and to avoid a potential collision with Titan, one of Saturn's moons. During the Saturn orbit, Journey 1 also discovered 4 additional moons: Mimas, Enceladus, Tethys, and Dione. Following the Saturn mission, researchers decided to conclude the Explorer planetary mission and sent both Explorer 1 and Explorer 2 into the solar system at a speed of 325 million miles per year. In January 1990, the Pristine mission, officially known as the Explorer Interstellar Mission, began. The most notable images and records depicting the solar system and its planets were taken by Explorer 1. On February 14, 1990, at a distance of 6 billion kilometers from the Sun, scientists noted that the solar probe captured a total of 60 images, bringing the cumulative collection to 670, although Mercury and Mars were not visible for various reasons. Eventually, the spacecraft's cameras were turned off to conserve energy and memory before its journey into interstellar space. In addition to Explorer 1 and 2, NASA also operates the Pioneer 10, Pioneer 11, and New Horizons probes. On February 17, 1998, Pioneer 10 became the farthest spacecraft from Earth until Explorer 1 reached the interstellar environment on August 25, 2012. Although no other spacecraft were in sight, NASA did not publicly announce the achievement until 2013. By November 2018, each spacecraft had officially left the solar system, with Explorer 2 crossing the heliopause and entering the interstellar medium. Explorer 1 is now thought to be 14.5 billion miles away, continuing to provide fundamental data that no other missions have been able to deliver. Since entering the unseen region beyond our solar system, the spacecraft has spent most of its 45-year journey in good health. However, recently, experts have noted some strange anomalies in its performance. Explorer 1 is sending mysterious signals back to Earth, creating the impression that its remote location is quite unstable. There are strange bends in the data, although researchers had programmed Explorer to enter safe mode or signal an alarm if it became lost in space. So far, it has not done so, and its radio antenna, which transmits information back to Earth, appears to be functioning properly. Nonetheless, the insights currently communicated are ambiguous. The interstellar probe operates, taking orders from Earth and executing them, as well as gathering and transmitting scientific data. However, readouts from the spacecraft's explanation and control system do not accurately reflect internal conditions, according to NASA authorities. What is occurring? Every spacecraft venturing into interstellar space, including Explorer 1 and 2, carries a unique 12-inch gold-plated disc filled with sound and video messages as a backup in case an extraterrestrial species discovers it. The disc contains 35 Earth noises, 115 images, an hour and a half of contemporary Western music, and greetings from former U.S. President Jimmy Carter and former UN Secretary General Kurt Waldheim, among other items. These messages are kept in 55 different languages, allowing extraterrestrial beings to attempt deciphering the signals. The notion that the spacecraft is currently under extraterrestrial control has been quickly denied by scientists. Explorer's ability to function relies heavily on its antenna and communication control system, which continuously keeps its receiving antenna aimed at Earth, ensuring researchers can receive data. It also manages how the spacecraft is oriented. Engineers monitoring the situation believe the probe is operating correctly, adding to the current mystery. None of the safety features designed to protect the spacecraft from hazards have been activated. According to Susan Dod, Task Chief for Explorer 1, mysteries like this are standard for this stage of the Explorer journey. The spacecraft is approximately 45 years old, exceeding its anticipated lifespan. This aging factor also means that the engineering team is encountering standard issues in troubleshooting Explorer 1. The vast distance between us and the spacecraft presents significant challenges, and the spacecraft is around 14.5 billion miles from Earth. This significant distance complicates the process that the team must explore carefully. A recovery operation is nearly impossible given the current mechanical and logistical constraints. Explorer 1's unique journey has led it into the furthest regions of our solar system and into interstellar space, where it continues to travel, now far from us. Messages received from Earth travel at the speed of light and take nearly 21 hours to reach Explorer 1's distant location. Any orders or processing sent by the engineering team require a full 42 hours to be received by the spacecraft. This delay creates a monumental challenge for real-time troubleshooting and investigation. When Explorer 1 processes an order, any response or data it sends back to Earth will take another 21 hours to return. This means that two-way communication between Earth and the spacecraft takes an average of 2 days. Such delays make it extremely difficult to execute quick fixes or iterative troubleshooting methods, which are crucial for addressing complex technical issues. The engineering team must meticulously plan and execute each command, anticipating various outcomes and expected results. Unlike missions on Earth, where engineers can quickly send and receive instructions, the extended communication delays necessitate a more strategic and efficient approach. As we delve deeper into the cosmos, the significance of space exploration becomes increasingly apparent. Missions like Explorer 1 have not only advanced our understanding of the solar system, but have also served as a foundation for future exploration. The data collected over the years has profound implications for our knowledge of planetary atmospheres, magnetic fields, and potential habitability. One of the most critical aspects of space missions is their ability to inspire future generations. The images and discoveries made by Explorer 1 and its counterparts have captivated the imaginations of scientists, students, and the public alike. This fascination drives educational initiatives, encouraging young minds to pursue careers in science, technology, engineering, and mathematics, STEM. The legacy of Explorer 1 can be seen in the rise of educational programs and outreach efforts that aim to instill a sense of wonder about the universe. Moreover, advancements in technology spurred by space exploration have far-reaching effects beyond the realm of astronomy. The innovations developed for spacecraft have been adapted for various industries on Earth. For example, materials originally designed for thermal protection in spacecraft have found applications in firefighting gear and energy-efficient buildings. Additionally, the miniaturization of technology required for deep space missions has led to improvements in consumer electronics, medical devices, and telecommunications. Collaboration plays a vital role in the success of space missions. International partnerships, such as those between NASA and space agencies from Europe, Japan, and other countries, foster the sharing of knowledge, resources, and expertise. These collaborations have resulted in groundbreaking missions, including the Mars rovers and the International Space Station, ISS, which serves as a testament to what can be achieved when nations work together toward a common goal. The challenges faced by missions like Explorer 1 highlight the unpredictability of space exploration. The vastness of space presents unique obstacles, such as radiation exposure, micrometeoroids, and the vacuum of space itself. Engineers and scientists must continually adapt their strategies and technologies to mitigate these challenges. For instance, ongoing research into radiation shielding and advanced materials aims to enhance the safety and longevity of spacecraft. Looking ahead, the future of space exploration is promising. With the advent of new missions, such as the Artemis program aimed at returning humans to the Moon, and plans for crewed missions to Mars, humanity stands on the brink of new discoveries. These missions will not only focus on exploration but also on sustainable practices that ensure we can live and work in space for extended periods. Moreover, the potential for discovering extraterrestrial life remains a tantalizing prospect. Missions like the James Webb Space Telescope are designed to observe distant exoplanets and analyze their atmospheres for signs of habitability. These efforts could lead to groundbreaking revelations about life beyond Earth, fundamentally altering our understanding of our place in the universe. In addition to planetary exploration, the study of cosmic phenomena, such as black holes, neutron stars, and dark matter, continues to expand our comprehension of fundamental physics. Observatories on Earth and in space are now more equipped than ever to collect data on these enigmatic entities, providing insights that challenge existing theories and inspire new lines of inquiry. Furthermore, the democratization of space is becoming a reality. With the rise of private space companies, such as SpaceX and Blue Origin, access to space is increasing. This shift not only enhances competition but also accelerates technological innovation. As commercial spaceflight becomes more common, the potential for tourism and research missions for private entities grows, paving the way for an era of exploration that is more inclusive and diverse. Finally, as we venture deeper into the cosmos, ethical considerations come to the forefront. The exploration of celestial bodies raises questions about planetary protection, contamination, and the preservation of extraterrestrial environments. As we strive to unlock the mysteries of space, it is essential to approach these endeavors responsibly, ensuring that we do not disrupt potential ecosystems or alter the natural state of other worlds. Every command must be carefully crafted to resolve perceived issues without introducing new problems. This requires great attention to detail and validation of commands on Earth before they are sent to Explorer 1. Despite these logistical challenges, the spacecraft is over 40 years old, having been launched in 1977. The age of the system does not, however, consider current needs. The engineering team must work with systems and designs developed in the 1970s, adding complexity to the troubleshooting process. The harsh environmental conditions of space have also impacted the spacecraft systems. Explorer 1 has been exposed to significant radiation, extreme temperatures, and micrometeoroids for more than 45 years, contributing to wear and degradation of its components. This makes maintenance and repairs considerably more difficult. Nevertheless, the engineering team remains committed to resolving the current issues, investigating various theories regarding the cause of the anomalies and evaluating potential responses through simulations on Earth. This careful and deliberate approach is crucial given the stakes involved. Any erroneous order could exacerbate the situation or lead to a loss of communication with the spacecraft. The CFT team is also utilizing the redundancy built into Explorer 1's designs. Like many other space missions, Explorer 1 was designed with backup systems to enhance resilience against failures. The engineering team can switch to these backup systems to restore normal operations if a critical component is found to be failing. In summary, while the challenges in diagnosing and resolving the issues with Explorer 1 are immense, the engineering team is applying their extensive experience and the spacecraft's inherent flexibility to address the problems. Their careful and patient approach is crucial in managing the lengthy communication delays and the complexities involved in working with a spacecraft that is both relatively remote and significantly older. Regardless of the odds, their efforts continue Explorer 1's legacy of exploration and scientific discovery, far beyond its original mission boundaries. The breakdowns may result from cosmic rays affecting the spacecraft's delicate electrical systems. These high-energy particles, originating from distant supernovae or other astronomical events, travel through space at nearly the speed of light. When they strike Explorer 1, they can penetrate its exterior and impact internal electronic components. The longer the spacecraft remains in space, the greater the likelihood of cosmic rays affecting its systems over time. This phenomenon can lead to sporadic glitches like the ones currently observed in Explorer 1's telemetry data. Specialists have long recognized the potential risks cosmic rays pose to spacecraft electronics and human adventurers, but predicting or mitigating their impact can be challenging. Despite these risks, engineers have implemented various methods to shield spacecraft from cosmic rays, including protective shielding, redundant system designs, and error-correcting codes in data transmission.